So good afternoon to most of you, or in the case of at least one of you, I know, good morning. My name's Pat Canning, and I'm with USDA's Economic Research Service, and I'll be introducing today's symposium. On the screen now, you should see our agenda. There will be 5 presenters, and so my job is to ensure that we have 30 minutes at the end for open discussion, and that means that I'll remind each speaker at 10 minutes, and hopefully I won't have to, but if you, when we reach 12 minutes, I will gently remind you that your time's up so we can move on. Because of the time constraints, we ask that you limit any comments during presentation to requests for clarifying material that you may not have followed. So hopefully you should see now on your screen the short biographies of our presenters, facilitator, and myself. Since I only have 5 minutes for this introduction, I'm just going to display that and invite you to read through the biographies while I give you a quick overview. Starting about 5 years ago, ERS and our research partners initiated a comprehensive study on the linkages of American diet outcomes to resource use and environmental impacts from the food system that accommodates those diets. And we produced a series of journal articles and some research reports out of the study. And our first speaker today is going to highlight some of that work. By 2018, ERS started to explore the possibility of providing annually updated estimates of food-related resource use linked to annual food dollar expenditures. And at that time, I was collaborating on other research with Miguel from Cornell, and we found that our institutions had a mutual interest in studying food supply chains and the role of natural resources in the environment. So we entered into a cooperative research agreement to jointly develop protocols and best practices for estimating and reporting data on this topic, and to develop applied research using this data. 2 of our speakers are going to report on some of this work. And also in 2018, my former colleague and now University of Hawaii member, Sarah Rehkamp, and I were invited to a food, energy, water data modeling workshop. This was a USDA NEFA funded grant, and it was hosted at North Carolina State University. And the goal there was to bring together a transdisciplinary group of researchers working on the FEW nexus, both to network and to brainstorm. And at the meeting, we did meet a number of people with strong synergies to our research area. And this included Michael Wang, who leads a research team with Argonne National Laboratories. That, well, they can better describe their work, and a couple of those team members will be speaking today. And we're now actively engaging with that team on collaborative research. Late last year, Cornell, Miguel and I organized a 2-day FEW workshop along the lines of the one I just described at North Carolina State. And that produced an even wider network of research synergies. So today's symposium really represents us going to this well again, see if we are still at a point of increasing returns to networking. And so after our 5 presenters are done, and provided we do have an audience along the way, Miguel is going to facilitate an open discussion. So with that, let me stop sharing my screen and turn this over to our first presenter, Sarah Rehkamp.
Hi, everyone. Thank you, Pat. Let me start sharing my screen. Bear with me here. Oops. Let's see. Okay. Okay, does everyone see the slides here?
Yes, yeah, they're there, Sarah.
Oh, okay, great.
Yeah.
Thank you. Yeah, thanks for the introduction, Pat, and thank you everyone for joining us in this organized symposium. So I am Sarah Rehkamp and presenting today on top-down life cycle assessment approaches to food, energy, and water research. So in our work, we are broadly interested in the topic area of sustainable diets, and two research questions really drive our work in this area. So I have them here on the screen. Do diet choices affect more than just health outcomes? And also, will resource scarcities threaten our food security? So we're considering the trade-offs and interrelationships between food, energy, and water. First, I'm going to focus on the food production side and discuss the methodology that we use to measure resource use in the food system. Our tool to estimate food system resource use is FEDS, an acronym for our Food Environment Data System. FEDS is both a data system for measurement of the US food system and is also a platform to build models on for policy analysis. We use an environmental input-output model, which is the top-down approach since it measures all transactions throughout the US economy at the industry level. FEDS allows for measurement of both direct and indirect resource use. Sometimes we call this embodied or total resource use. And the example I typically use is the embodied water in beef. So water is directly used for the cattle's drinking and servicing water, and water is indirectly used to irrigate crops for the livestock feed. We can measure both monetary and environmental flows using this framework. Those that we've worked with, I have listed on the slide here, and this includes the energy and water metrics that we're most interested in for this symposium. So this approach, compared to a process-based or a bottom-up life cycle assessment, is consistent in the way each resource is measured and is also country-specific. FEDS follows the framework adopted by the United Nations Statistical Commission. So a system like FEDS could be developed by other countries that follow the UN accounting framework. Our focus is on the food system, and this means we're able to capture salient attributes of the food system that are obscured in the national accounts. So an example of this would be the energy use in the cold chain to get perishable food to the consumer. And finally, I wanted to mention that we build the data up from the county level. So we're able to capture geographical heterogeneity, and we're also building the data up over multiple time periods as well. This slide shows visually the boundaries of our analysis. We include the embodied resources from farm inputs through household consumption. So this differs from other life cycle assessments. Some exclude the household consumption stage and just conduct their analysis through point of purchase, or some others do cradle to grave analysis, and that would include the post-consumer waste. Again, these boundaries are consistent for energy, water, or any other metric using our EIO life cycle approach. This chart is from a recent publication that we had showing the share of estimated total resource use in the US food system by supply chain stage. These data are reflective of consumption in the United States from 2007, which is the same year of our most recent model. And what I'd like to highlight here is a freshwater withdrawals bar, which is the fourth from the top. We see that the majority of food system water is used on farm, which is due to irrigation. This is something we might expect. However, energy services uses 12% of food system water, which is shown in yellow. You can see explicitly the food, energy, water nexus, and this section represents the water used for energy production throughout the food system, such as cooling water used at thermoelectric plants. Now, I'd like to touch briefly in the second part of this presentation on linking the supply side to demand or food consumption choices. Many other studies consider diet or the demand side in terms of farm level commodities. However, commodity is very different from the foods that ultimately end up on our plates. The caloric shares by food group shown here come from the National Health and Nutrition Examination Survey, or NHANES. These are dietary recall data, and respondents report the food and beverages that they have consumed in the past 24 hours. The pie chart shows the caloric makeup of the average American diet, and you can see in the legend there, these are groupings of the 4,000 plus unique food items reported in NHANES. In the light yellow section, you can see that grain products make up 35% of the calories in the average American diet. We link the individual food items that make up the average American diet to the environmental input-output model for an integrated sustainable diet analysis. So in the center, you can see the Q matrix, and we rely on the Q matrix to bring together the EIO model for resource use on the production side, and then the diet optimization on the consumption side. So said in another way, we're translating the commodities as purchased to food items as consumed. To illustrate this, I've included an example of a peanut butter and jelly sandwich shown at the bottom of the slide. The sandwich is the food item as consumed. You would need to buy the 3 ingredients in the first column, the bread, the peanut butter, and jelly, to make the sandwich. Ultimately, this approach of linking the two models allows us to estimate the resource requirements by specific food groups. So again, I'm showing our results on freshwater in the US food system. And this slide, if you look at the y-axis, we have those food groups and the total water withdrawals broken up into supply chain stages in the bars. Our results show that meat, poultry, and fish use the most water. These results are based on the amount and types of foods consumed in this category in the average American diet. It doesn't necessarily indicate that this is the most water-intensive food category. And what I like to highlight again here is that energy services, which is now shown in the blue color, is a top contributor of water across the different food categories. Also, if you recall from the earlier slide, grain products contributed 35% to total calories, but grains use about 21% of diet-related water. So there's a disproportionate amount of embodied water compared to calories for each of these categories. In addition to the top-down approach of the EIO model I described, we've recently have begun work to develop a multi-regional social accounting matrix, or SAM, which is an extension of the EIO model and will allow us to better understand the food system at a subnational level. We're planning 2 state-level case studies for Hawaii and New York, since we have the University of Hawaii and Cornell University represented on our FEDS team. These states are also both interested in self-sufficiency, and will have differing supply chains that will make the 2 states interesting to compare. We've discussed also decision-making tools in an effort to reach a broader group of stakeholders with this work. And finally, we're interested in growing our team, collaborating with others, and we hope to engage with you all for furthering the work in this area. So thank you so much for your time. Here's my email address if you have any follow-up questions. We look forward to participating in the discussion with participants here in a bit, and I'll just put the references here before I stop sharing.
Thanks, Sarah. That was 10 minutes on the dot. Good job. Let's go ahead then and go to our second presenter, Uisung Lee. please proceed.
Do you see the screen?
Yes.
Okay, sounds good. So let me get started. So hello, my name is Uisung, and I'm an energy systems analyst at Argonne National Laboratory. So today I'm supposed to talk about the bottom-up LCA approach, life cycle analysis approach to the food, energy, water research. So I brought our research in LCA using the grid model representing the bottom-up approach. Since I only have 10 minutes or so, I will deliver the high-level research summary explaining our efforts at Argonne. But if you have anything to discuss, maybe we can use a discussion session, or you can send me an email afterwards, then I'll happy to discuss the details. I'm sorry, I cannot move to. Yeah. So some of you might have heard about the Adopt Grid Act. Like actually, I found this from a news article like only this week. So some senators proposed legislation to require the EPA to update greenhouse gas modeling for ethanol and biodiesel using grid model. So you may be wondering what's grid. So, and by the way, right? So the name grid comes from a long name, which stands for greenhouse gases, regulated emissions, and energy use in technologies. So it was developed by Argonne National Laboratory in 1995, and since then, a group of researchers annually update and expand the model. So although the model itself initially was developed to analyze the environmental impact of various energy systems, including transportation systems, like after around 25 years of effort, now the model is capable to analyze various sectors such as food and water systems. So here is a link of that, our website that shows the model and all the publications that we made. So you may want to visit the website. So currently there are 43,000 registered grid users globally, mostly but not limited to automotive industry and government agencies. So the grid is used for making some of the carbon intensities, estimating the carbon intensity for the EPA or the California's Air Resources Board. So this is a gold standard of evaluating various energy system sectors, which is why the senators asked EPA to use the grid model, which is basically based on the most up-to-date data sets based on Argonne's extensive research effort. So again, the grid model started from analyzing the energy sector, in particular transportation area. Since evaluating the environmental impact of biofuels, which is one of the key priorities in grid model, we have extensively collected and implemented various agricultural data sets, which are the major part of the grid model. So through the efforts, we found that water has its own research issues, such as water stress of water or water quality. So we have expanded the model to cover the water consumption, as well as later on we developed the water stress index, which is called AWARE-US. And my colleague Hui will explain the AWARE-US in detail in the later presentation. So the grid model is bottom up. So let's say configured process by process. So when we evaluate the biofuel pathways, we collected significant agriculture-related data sets, including fertilizer use, crop yield, logistics, which can be also used to analyze the environmental impact of food or feed. So I'd like to emphasize that the grid is capable of analyzing three major sectors: energy, food, water. So using the grid model, we can basically quantify four major metrics. namely energy use. That includes total energy, fossil energy, or renewables, right? The fossil energy itself includes petroleum, natural gas, and coal. So we can evaluate the life cycle energy use. And we also generate air pollutant emissions and greenhouse gas emissions. Water consumption is part of the grid results, and then the water consumption results can be used to analyze the water stress impact. So, and also we do have the multiple functional units. So the results can be expressed in terms of the energy or the services or a ton basis, like a ton of food or feed. I emphasized like several times that the grid has extensive data sets, and all data sets are from the research efforts at Argonne. So, and we, like in addition, we documented all the data sources and how we processed the data in a technical report or a journal paper or in a memo so that everyone can track back to the sources. It means each parameter is like supported by extensive research effort. So if you like check the if you check the grid website, you can find all the data sources. And this slide specifically shows how we typically collected data. And for example, we rely on USDA, the data set to cover the field operation data, along with others like the simulations or the collaboration with other laboratories. And grid includes more than like 100 fuel production pathways, including fossil, both and fossil and biomass pathways. And each pathway includes multiple processes. And you may identify that we do have many biomass feedstocks, so the feedstocks to fuel production pathways. So which can be also used as food, for example, or feed. And I have just mentioned that each pathway, like pathway means that the fuel production pathway has multiple processes underneath. For example, when you analyze an ethanol production pathway from corn, for example, we consider corn production that includes all fertilizer use, and the fertilizer starts from the fertilizer production, including the raw material for the fertilizer. And we also consider all the energy use for the feedstock production, which is farming, harvesting, and transportation, etc. So, as I mentioned, we do cover the energy system. So this is a typical results that we can generate using the grid model. And this is an interactive website that shows the major grid results. And you may see that the greenhouse gas emissions, energy use, air pollutant emissions, and water consumption could be presented in terms of the functional unit that the user selected. Maybe while these are all like fuels mainly, as I mentioned, we can use the grid's extensive data sets for the performing LCA of various systems. And I will show you one example here. It's a one like emerging pathway in grid. So this is about the animal feed for swine and poultry production. So this specific study shows the environmental effects of the animal diet changes. So when the animal diet changes from the baseline to scenario A, B, C, then how it's going to be the environmental impact will be changed. So as you may see, we have the functional unit of the kilogram live weight animal at the farm gate. So you may see the greenhouse gas emissions or water or energy use could be evaluated, quantified at the designated functional unit. And here is a sample example for this specific case, which can be found from this the recent publication. So you may see that we can generate the results for the greenhouse gas emission results, for water consumption results, for each ingredient, for example, soybean or corn or amino acid here, GGS and amino acids here. And water consumption has the soybean and the corn has much higher than others. But these are for the specific one ingredient, each for ingredients. So you may see the amino acid has the highest greenhouse gas emissions because it's a high energy intensive production process, and water consumption, we do see the high water consumption for soybean and corn. But if we integrate these to the diet share, because the amino acid has a little share compared to others like the DGS, the impact will become smaller. So by combining these impacts with the share of each ingredient, we can generate the life cycle greenhouse gas emissions or water consumptions in terms of the kilogram of animal feed. Similar research can be done for the food or other like systems.
2-minute warning.
This is what. Yeah. So again, I just want to deliver the key highlights of the grid model. So if you have any specific questions, you can send me an email. Then I'll be happy to answer your questions. Thank you.
Thank you. And again, as Miguel noted in the chat, you can post your questions on the chat, and we will have time at the end to have a discussion. Frank, I think it's your turn.
Yeah, let's share my screen. So do you see it? My screen?
Yeah,
yes, looks good.
It's there.
Yeah. Hello, everyone. Yeah, I'm Frank Ge. Yeah, my presentation title is the carbon footprint of flesh produce assembly and distribution in the United States. Yeah, climate change is one of the most pressing challenges, and greenhouse gas emissions is one of the major causes of global warming. As we know, food is responsible for 1/4 of the world's greenhouse gas emission. So this study, we focus on greenhouse gas emission in flesh produced supply chain system. While there are widespread attention to greenhouse gas emission on the production side, less attention are paid to flesh produced transportation footprint. Americans consume a huge amount of flesh produce. So the total amount of greenhouse gas emissions from transportation is very large. So assessing greenhouse gas emissions from transporting flesh produce contribute to environmentally friendly agricultural policy development. So the objective of this study is to assess the flesh produced greenhouse gas emission associated with produce aggregation and distribution, and explore possible ways to reduce transportation footprint. Hopefully, this study can provide a basic framework for our next step study for our project, Capacity for Food and Energy Water Research. In this project, life cycle analysis of water and energy use in flesh produced supply chain system is the focus. So this study is just a start point. In this study, we don't simply assess greenhouse gas emissions using empirical flesh produced transportation data in the United States. Instead, we solve a food hub optimal hub location model to identify the optimal flesh produce assembly and distribution patterns, and then calculate the greenhouse gas emission associated with produce assembly and distribution. So the model offers a way to incorporate a supply chain system uncertainties, which allows different environmental or economic variables of the system to enter the model. This facilitates conducting sensitivity analysis on how the supply chain performance responds to change in the operational environment in the supply chain system. The optimization model minimizes the cost of hub setup, product assembly and distribution, and product handling. This model is subject to several constraints, such as production seasonality and category segregation. The model will trace the movement of different categories from farms to consumers by month. Marketing cleaning conditions requires all imported and domestically produced fresh produce will be transported to export port or to domestic consumers. The model also considers scale effect. That is, the hub handle higher quantity of products could have a lower per unit handling costs. Our model will balance the trade-offs between costs and benefits and determine where to locate hubs and what scale type those hubs should be. In this study, the hub location problem involves a large-scale optimization model. To reduce the model complexity, we categorize about 40 highly perishable vegetables and fruits into 9 categories based on their similarity. This figure shows the monthly distribution of fresh produce production and import. Production and imports vary across months. This figure shows the continental distribution of fresh produce production and import across US counties. The production and import is not evenly distributed. We need to solve the model for the best way to consolidate those products and distribute them to destinations by category and by month. Next, we show our model results. This figure shows the solution for 82 hub locations. We compare the locations and scales of the modeled hubs with the actual hubs in reality. The simulated hub location display very similar pattern to actual hub locations. So the modeled locations seem to effectively reflect the actual hub system. So this table shows the relative costs of the system. Transportation accounts for about 45% of total costs. The average transportation distance is about 1,000 miles. Distribution distance is over 900 miles. It's much longer than the assembly distance, 63 miles. This figure shows the assembly pattern of 82 hubs for all categories within 12 months. This figure shows the distribution pattern of product. The distribution patterns significantly differ across categories and across months. As an example, here we show the distribution patterns for 4 categories in August: starch vegetables, other vegetables, starch vegetables, other vegetables, tropical fruits, and stone fruits. Based on the transporting patterns, we calculated the transportation distance from farms to hubs and from hubs to consumers. Those 2 figures show the transportation distance in August. Stone fruit categories is on the left. The average of all categories is on the right. Transportation distance in California and in Northeast are lower than in other regions. It seems that the regional transportation distance is negatively related to regional production. Based on the transportation distance and consumption level in regions, we calculated the total green gas emission at the county level. The left figure shows the green gas emission from shipping stone fruit in August. The right figure is for all categories. As the figures show, metropolitan areas have larger green gas emissions. Los Angeles and New York are among the highest, despite the shorter transportation distance. The huge amount of consumption in those cities due to higher green gas emissions. Chicago is also highest because its consumption heavily relies on imports from other countries far away from the city. Rocky Mountain states and some of the Midwest greenhouse gas emissions are lower due to the lower consumption levels. Also, the transportation distance is longer. So there are some discussions. As we know, transportation costs account for about 30% of the wholesale price. So reducing costs and reducing the carbon footprint may work in the same direction if reducing transportation distance won't increase other costs, or reduced transportation costs are less than increased in other costs. There are many ways to reduce the greenhouse gas emission from transportation, but we discuss this issue in the agricultural adaptation domain. Land use change may help mitigate emission. That is, to expand local production for those regions where suffer consumption deficit, such as the Midwest, Rocky Mountain states, the West, South Central. Expansion of local production enables people eat more local and thus reduce imports from other regions. Then greenhouse gas emissions from transporting products can be mitigated. Given land use pattern, planting and harvesting may help smooth the production and narrow down the gap between demand and supply in a region. For example, farmers can harvest earlier or postpone harvesting corresponding to demand. Normally, incentives to change the planting or harvesting plan is to reap the benefit of higher prices. This incentive could also work for greenhouse gas emission reduction because higher fresh produce prices likely appear when there is a shortage of fresh produce supply. Production expansion is dependent on land availability and productivity and water stress. So expansion production of a crop in a region may lead to higher production costs than growing the crop in other regions. So this may make the production expansion plan not economically applicable. But if we take environmental benefit into consideration, the answer can be different. So sustainable agricultural policy needs to balance economic sustainability and environmental sustainability. How to link economic and environmental sustainability in our models is a challenge we face. It also represents our research and modeling direction in the future. I believe next Fee will offer more descriptions and discussions on this issue. So any questions, please contact me. My contact information already listed in the slides. Thank you.
Thank you, Frank. You got in there just under 12 minutes. Nice work.
Thank you.
Your turn.
Hello, everyone. This is Hui. Can you see my screen?
Yeah.
Okay, great.
Yes.
So we'll talk about two examples relating to how we can link biophysical models to economic models for water impact assessment. This is a broad topic, and I'm not intending to cover everything, but just give you two examples about the kind of tools we may have to address at least partially this issue. So same with Uisung, and I'm working in the System Assessment Center at Argonne National Laboratory. So this is a quick outline. So we will talk about two sides of the water impact. One is the water stress. It's more like a quantity. Do you have enough water or not? The other is the water quality. Both are important depending on the objective of certain research. So we will go through both case studies, but with focus on the aware US that Uisung briefly mentioned. So how we can quantify water stress impact of biomass production, energy production in a spatial explicit manner. So several talking points. So we know the water consumption itself has a limited meaning, right? One example is that I was having a meeting in Sacramento last year. People in California are talking about the drought and the problem they may need to reserve water. However, people from South Dakota said, we have a flooding there. The soil is too wet for them to plant corn, so they have too much water issues. So with that, if we are simply talking about water consumption without having understanding of the underlying context, then the result might be misleading, especially when you're trying to mix dry region with wet region together. See, here's the average water consumption, and we don't have any water stress issues. So that could be misleading. As I mentioned, the regionality is really a key issue. It really depends on where and when. So with that in mind, Argonne recently developed a water stress impact assessment model. It's called Available Water Remaining for the United States. It was inspired by the AWARE global concept that was proposed by United Nations Environmental Program. But we took that concept and developed a county-level monthly step water stress model specifically for the United States. And this animation just showing at each county how the water stress status can change from month to month and have different spatial patterns. So briefly, we use the characterization factor or the CF factor. It's kind of a standard method in life cycle assessment. We're typically using CF to quantify the marginal impact of water consumption, the unit of water consumption. What is their impact in location A versus location B? So if CF equal to 1, that means I have the average equivalent impact in the US. If it's greater than 1, means you have less water than the US average, so you have a high impact. If the less than 1, like the 0.1, means you have much more water than the US average, so the marginal impact is smaller. So in general, we see the Eastern US, they tend to have more water, so they have a green color. But in the high plains region and the Western regions, they have less water, and their color are more brown and the red issues. But this also really depends on the season. For example, in the California, they're not always red. It really depends on the season. Okay, my screen is a little bit frozen. I try to, okay, let's try to stop video to reserve the bandwidth. Okay, this will be better. So on the left, we see it is a map. It's an example of application using AWARE US to algae production. On the left, we see two maps. The first map is showing the algae biomass yield in the different potential sites in the United States. As you can see, it really depends on the location, and usually if you have a higher sunshine temperature, you have a high yield. And their water consumption ratio, that means how much water we need to produce 1 liter biofuel from algae. It also varies substantially across regions. And on the right, we see if we rank all those sites based on their accumulated, based on their marginal water stress impact, which is quantified using water scarcity footprint. Water scarcity footprint, as I mentioned in the previous slide, it is a product of the AWARE US water stress factor and your water consumption. So when we rank the sites based on from the lowest to the highest water stress impact, we can see the differences are very significant across the regions. Meanwhile, if we're just looking at the this line, this is showing the biomass yield. The variations across regions are much smaller compared to their water stress impact. And that means there are plenty of room for spatial planning. We can pick up sites with good biomass productivity without placing them in areas with really high water stress impact. Okay. So previously we mentioned the spatial differences. Now we want to show that the water stress impact can also vary seasonally, even though they may in similar regions. So here are four example counties distributed around the Gulf of Mexico area, from Texas to Louisiana, and even in the same state, like Florida. We generally believe Florida, they have too much water maybe because they often have hurricanes. However, when we think about the seasonal in April or May, like Miami County in the southern Florida, they literally have little remaining water because the precipitation, it's kind of a drought season in the spring for South Florida. They do not have enough water in this particular time, even though they have plenty of water in September when or August, when you hear the hurricane is coming, but it doesn't really help the spring drought issues. And as we can see, both the demand and the supply, the seasonal patterns vary significantly across regions. So that's why we need to consider both spatial and seasonal variations. So with that in mind, this is an example. If we want to produce like 30 million metric ton algae biomass, then how can we select the site? So we tested with different criteria. We can just select the sites based on the highest productivity, and most of them will be located in South Texas and with a little bit in South Florida. And the issue is that those selections will result in very high water stress impact because the coincidence with counties lacking of fresh water. Or we can say, how about we just select sites with the highest water use efficiency? That's a conventional concept. And that way we will select most sites in Louisiana and with some in North Carolina. The issue is that they tend to have lower biomass yield. So economically, this is not a competitive solution. If we place Aware-US on top of productivity, then we can select a site that can avoid high water stress impact, but also we can keep those sites with really high the yield. Of course, there's a trade-off, and this graph just showing that how would you like to prioritize biomass versus water stress and water consumption, right? And there's no clearly yes or no answer. It really depends on how would you like to prioritize. And our suggestion is that if we do a mix of those kind of find middle ground, for example, find area where the annual CF is less than 1 and the monthly CF is less than 15, we can achieve really significant reductions in both water consumption, the water stress impact, with less than 2% reduction in yield compared to the optimal scenario where you thoroughly focusing on the yield. And here's the example. If you're interested in using the Aware-US model, we have a website. You can go to the website and pick a county or a state or either annual or monthly, and then you can enter your consumption data, and then the model will calculate the monthly water scarcity footprint for you automatically.
2 minutes.
Okay, I'll finish this quickly. This is another example. I put it here because probably more relevant to economics. We know in Lake Erie, they have a recurring algal bloom problem. A lot of efforts have been put into conservation practices focusing on agricultural land. I'm suspicious of this solution would actually work. So to prove my hypothesis, I've developed a integrated modeling work. You have hydrological model and you have economic modeling. The idea is to compare what if we also consider land use change, convert some of the corn soybean fields to less fertilizer intensive use, alpha hay, forest, grassland, for example. And the result, I think all the audience are pretty familiar with the Pareto frontier or the efficiency frontiers. So I will not explain that here, but briefly, each stat means the best combination. Or if you really want to reach a certain percentage reduction in phosphorus pollution, then what is the best annual net returns you can get through this combination? What we see here is this yellow line means the reduction in dissolved reactive phosphorus, DRP, which is really a key in the Lake Erie region. Even if we put all combinations throughout all agricultural land, the best you can get around 60%. That still falls short the target, 78%. The US-Canada joint target. So there's no way for you to reach that goal solely focusing on conservation practice. Some kind of land use changes are necessary. If we can combine both conservation practices and the land use changes together, then we can simultaneously improvement in both nutrient pollution reduction and economic returns. Part of the reason is that we pay farmers to grow corn and soybeans regardless of the productivity. Also, if we take out those subsidies and consider that kind of another direct payment to the farmers, then we can see some areas are better to be converted to alternative uses. And
we're at 12 minutes. If you could just wrap it up.
Okay, yeah. So that's it. If you have any questions, feel free to reach out to any of us, and we'll be more than happy to discuss this research and the tools. Thank you.
Great, thank you. And I'm really excited about being able to work with that model and our past MP produce model. Jing, it's your turn.
Okay, so hello everyone, this is Jing. While I'm sharing my screen, let me start talking. I'm a research associate at Cornell University. Today I'm here to present the fantastic data system and applications we have been developing to disseminate findings to different stakeholders. Although I'm here to present, it's truly a teamwork. So this diagram, I think it's not showing you over there. Give me a second. There. So this diagram shows the framework of the food environment data system. Data were collected from different sources. Our team developed different models and algorithms to create value-added data. The source data and the value-added data are stored in our cloud-based SQL server. You can think the cloud SQL server as a website. Anyone with an account can view and use data that is stored on the server. You can also hook the SQL server with your analytic software, such as R, SAS data, to import data into your program directly. And based on the SQL server, we developed a series of applications, such as web applications. Users can go to our web page to view the charts, tables we created. Since the web page are linked with our SQL server, each time when we update the source data and our model, the results automatically or manually update the data in the SQL server, and that will automatically update our front-end table and the charts. Those web applications are very useful to disseminate our research findings to various stakeholders. Users can view the charts, download the data, and download the selected charts from the web page. You can also use SQL Management Studios or any other query tools to get data from our SQL server. Like I just mentioned before, it automatically grabs data from the server and update your results when you run the model. You do not have to manually download data. Our SQL server is just like your data folder, except that you do not have to manage it. Of course, we developed a series of research projects on top of the data we created. We also constructed online documentation and the tables to support the use of the data. For example, each time when we update the data, we publish a technical note to introduce the updates in the new version. So next, I'm going to use one of the web applications we have been developing to illustrate the whole picture of this best project. So the water use web application is one of the natural resource module to show how much natural resources are used to make and market the products purchased by a food dollar. The food dollar basically is $1 that you spend on domestically produced food. Let's use milk as an example. You can use this water use module to see how much water was used to produce $1 of milk at each food supply chain stage. So as we shown on the first slide, we collect data from different sources. And in this case, the primary data source is US Geological Survey data. The USGS survey data are aggregated data. It shows the blue water used by different categories, such as irrigation, industrial, and public supplies at the county level. Along with other supplementary data, Pat and Sarah disaggregated the water use data to North American Industry Classification System, which is NICS. So we know how much water was used to produce a specific commodity by a specific industry. Then after that, we can aggregate water use data by different standards, such as different food categories, different supply chain stages, or geographic levels. So now you are looking at a screenshot of the FED server we have. All the source data and the value added data are well organized in the server. All the collaborators can link to the server and use the data. And our front-end web applications also linked to the server to show the data on the front page. Since we disaggregated water use data to NICS, the final data we have are multidimensional. We can view the water use data from different dimensions, such as different supply chain stages. On the web page, users can select different natural resource modules. They can download data behind the chart, or they can even download the charts. So next, I'm going to bring you to the website that we have here. Did I share my screen?
Yes, you're good.
Yeah.
We can see the presentation.
Thank you very much. So here is the landing page of this water use module. On the top, users can select different natural resource. Now we are looking at the landing page of water use. You can also select the energy, land, greenhouse gas emission, etc. We developed this top panel to provide a general idea of water use in the US food system. We compare the US food system water use with other countries. We aggregated the US food system water withdrawals by supply chain stages. And also users could select different food categories. For example, you can select to see how much water was used to produce the market fats and oil, beef, cereals, etc. We have some other similar web pages like this, but I'm going to bring you to this web services we developed. So on the top, users can select different water categories, such as livestock, mining, irrigation, industry. Now we are at irrigation, and you can also break irrigation water use by water source, such as groundwater, or surface water, or total. We have different years data, but here you could let it play like a movie to show the change over time. And that shows you the water irrigation surface water use over time. And when you move your mouse over, it shows detailed information of each selected point, and also you can Google an interesting address like Google Map. So let me go back to my slides. Like I mentioned earlier, we have supporting system to support the use of data we have. We have online data catalog to list hundreds of tables we have in the SQL server. And we have online documentations to show you all the details you would like to know before you use the table. And we also have like a detailed technical note with each update to show you the updates in each new version. So to sum up, we have cloud-based SQL server, we have SQL reporting services to generate those interactive tables and charts. We have Tableau to create a fantastic visualizations, and we have web applications developed on top of those resources we have. So since we already built up the system, it's quite easy to add additional functions or components into this platform. For example, to meet the emerging need for research on the US food supply chain, recently we have been developing a series of studies to analyze the impact of COVID-19 on the US food supply chain system. And based on the results, the modeling results, we developed some map services like this one. So you can select a different, basically those charts show you how highly perishable fresh produce were transported from production areas to food hubs and from food hubs to markets. And you can select the different categories to view the information, and also you could select the different food category, different hub locations to view the data. I think that's it. Let me check. So where's my slides? So I think that's it. That's it. I'm done.
Thank you, Jing. My name is Miguel Gomez, and thank you for the excellent presentations. I am part of the Cornell team working on the FEDS project and collaborator with many of the presenters. So I will be moderating the discussion, and I see that a few specific questions that were posted in the chat that were more clarifications were already addressed. So I would like to take this half an hour to discuss, to open for questions from attendees, and also to discuss ways in which these modeling efforts can be used to understand pressing issues in the food system in the US and beyond today. Okay, so perhaps if there is, please, we are not too many, so you don't need to send your questions through the chat. So just unmute yourself and you can ask your questions. And just to start, I perhaps can start, and I would like to ask a question for Sarah on the work that you presented, and I'm just very curious, given, for example, because this is about healthy diets and how that will impact the use of resources. And I wonder if this type of approach may be appropriate to model things such as new technologies that are new food products, such as the meat plant substitutes that are becoming very popular, that are using, of course, crops to produce this. There is a huge innovation in that area. So I think question for you is, can your type of approach start looking at this, this changing in not only in diet, but also in the composition of foods offered to the market, such as in this case, given that the meat sector is a big user of many of the resources, including water. It would be interesting to see if you can see if consumer substitutes or if plant-based meat substitutes take over, as they are smaller, still a small portion of all the meat consumed. They are about 3%, but they are growing fast, and there are huge investments on that area. So.
Yeah, I agree. Thank you for your question, Miguel, that this is a growing segment of the market. So our approach and the work that we've done in the past, we have been able to look at, the average American diet is omnivore. So it's including meat products, other animal products such as dairy and everything. But we have looked at a vegetarian diet that would exclude the meat. And so we've done a number of scenarios in our work that are vegetarian, and that has implications for the resource use using this framework. But specifically with the plant-based substitutes, it was really interesting. So I recently looked at more recent dietary data from NHANES, and there's a lot of different changing products that are included in those dietary databases. In terms of the plant-based substitutes, I have seen papers that use the process-based life cycle assessment or more of a bottom-up approach to compare the resources used in something very specific, a very specific product like that, like the Impossible Burger compared to like the conventional beef burger.
Thank you, Sarah. I will give the opportunity to others to ask questions about to the presenters because I have a list of them, but I don't want to take over all the questions. Please.
I have a question, but first let me just add on a little bit to Sarah's answer to your question, Miguel. I mean, the plant-based analysis you mentioned is a classic example of where sort of the top-down versus bottom-up approaches have their strengths and weaknesses. To give you sort of a sense of the challenge there, when we model with environmental input-output, for example, we took great pains to break out in the model 74 different commodity value chains or supply chains, which is really far more than the basic input-output model allows for, but still is highly aggregated. And in order to accurately distinguish something like a plant-based alternative, we would have to augment the data with specific information and or doing some kind of hybrid type analysis with some bottom-up and top-down approaches combined. The analysis Sarah presented was using old 2007 data, and we are going to be updating that to 2017. We do have methods now to update the detailed model. So I'm really excited about the Aware US model. I've been ever since we met Michael down in Raleigh and have had subsequent conversations up in Ithaca and on email. Frank presented our phase one principally of our produce model, which is a monthly county level market clearing model for a number of highly perishable produce varieties. And with that, we can model not just harvesting, but even planting decisions at a detailed level. And we could link that to the Aware US in a way that would link these decisions with how they affect water stress as measured by the Aware US. And as long as there's some way to turn into equations, if you will, sort of variable decisions of the level of water use at time and space specifications, it would be a really nice application that I'd love to be able to delve into in the fairly, near term once we get this full model up and operating. And I hope we have a chance to talk more about that going forward. But I mean, so my question, to turn that into a question, is it typically the case that you can translate to some kind of behaved equations, like say smooth, convex or concave equations of water stress, or I like that measure you have for measuring water stress indexes that could lend itself to like a numerical models, things like that? Does that question make sense? And that goes to any of you.
Yeah, and Miguel, I have a response and a question.
Okay, you respond and then you ask the question. That's a good
okay, good. Yeah.
Thank you, Michael.
Let me respond to Pat's thinking to link Aware US to the world result from the model already there. I think that's your exact where the Aware US will provide additional insight. And as you saw from Hui's presentation, now we have county level, monthly water stress index, you have counted at monthly water consumption and well, maybe water withdrawal at county level at a monthly basis. So this is a great application to get water consumption to the next level of what water consumption mean. So the model with the additional improvement and the database building since we met last December, I think it's ready for linkage or applications. So let's find some time to talk at how to link these two together and to get you to water stress level from total water consumption. And my question is for ERS and Cornell in Jing together. So Frank's presentation showed from transportation and warehouse point of view, local definitely have benefit because that's where we reduce transportation and warehouse requirement. On the other hand, we know the production stage, the farming stage, productivity is very different in different US counties. That's why we concentrate in certain areas for certain fresh produce. So do you have the plan eventually to link production and logistics together to optimize the system to consider both? Because the productivity is different. On the farming stage, the logistics is different. Let's your lettuce is a good example. If we have California produce 90% of the US total amount of lettuce, they have their production, they have their productivity there. Versus now, if we produce in Illinois, in upstate New York, so where are we going to see the sweet spot when we have two together? Because to me, I think that's going to be very unique to the system level optimization.
And
of course, water consumption. So the water in California versus water in Illinois and in the upper state New York is very different.
Very different, yeah. So Frank, do you want to address?
Frank, you're muted if you're talking.
Frank, yeah.
Maybe while he's unmuting, I can sort of chime. Oh, go ahead. You're good, Frank.
Yeah.
Yeah, I think we can develop a model covers the, for example, food production, the entire cycle from production, transportation to marketing. Yeah, include the water stress, land availability and land productivity. Yeah, this concern about the optimal location of cropping pattern. Yeah, somewhere enjoy advantage to grow one kind of crop, other place probably suitable for growing other crops. So yeah, we are we work with Pat, Miguel, and our research group. We are think about how to consider land availability, productivity, water stress together to optimize the optimal production locations for different crops. Yeah, and also we link the production to our transportation system to see if the production location change, how the transportation system should be adapted to transport those products to consumers efficiently. Yeah, basically we probably focus on minimize the total system cost, but we also would like to link economic effect to environmental effect. That means we not only consider the benefit economic benefit, but also environmental, biological, biophysical benefit. We consider the external, social externality in our optimization model. So this model will very huge, yeah. Integrate different modeling skills, yeah, biophysical modeling, environmental modeling, economic modeling. We, yeah, require data from different sources: science, agricultural science, yeah, economics, yeah, many aspects. So, yeah, we need a cooperation, yeah, from researchers from different fields, yeah. So I think it's very hopeful. That's our research and cooperation direction in the future, yeah.
Thank you, Frank. Pat, do you have anything to add to that?
Just what I would say is there are two approaches. We could take this optimization approach, which is sort of to design an optimal system to minimize water stress of meeting the demands for produce. But another approach is an equilibrium approach, which gets at the classic issue of a disconnect between water stress and sort of market signals like price. People in water stress areas are not necessarily paying the costs of the additional stresses in their area, and therefore they won't optimally adapt for that fact. But you could, in our equilibrium model, we could look at, for example, introducing some kind of a cost tax, or maybe like a carbon trading, but for water stress trading, that would endogenize these costs and see how that might impact spatial equilibrium. And that would be a really interesting one. That's the kind of application I'd be really interested in delving into in this framework.
Yeah, and just to add to that, just briefly, so Binja and Dai, who is attending, she's going to be starting her PhD here. We have been working on a very simple model, but we have very detailed cost of production in different regions just for broccoli, as a part of a USDA effort to develop broccoli industry in the East Coast, and over the last 10 years, it is growing. The planting for broccoli are growing faster in the East Coast than in traditional parts like California and Arizona, and we still have also some import from Mexico. But we are looking at exactly. It will be wonderful for us to have a mechanism to. We are very interested in understanding. Okay, what if you really pay for the cost of water, because water is a scarce resource. If it is more scarce, price should go up. What will be the impact for the competitive advantage of the different regions? So I think this link will be to the water stress index that the Argonne lab is working on is very attractive to many of our modeling efforts here. Before I continue, Wes, I don't know if you want, Wes is from EPA, and I wonder if you have any question, comment. I saw that you posted a comment, or yeah, Wes, thank you. Go ahead.
No, I just wanted to thank everyone for letting us listen in. I appreciate it. I was just building on the one point. I mean, could you combine not just the water stress, which is not equally distributed, but also we saw all the diagrams on the carbon footprint based on transportation, and then some of the other indicators we have. I mean, could you make it some kind of multi-metric, index that reflected these costs that are not, in the market costs that you see, these environmental costs? Because I think at this point, we're getting to the point we can model a lot more. We showed water in a very detailed level, carbon, but yeah, we can get to eutrophication and other indicators we have in some of our models. So I mean, I guess ideally it would be some kind of multi-metric approach.
But
yeah, that's like the holy grail, really, of this kind of analysis, is an ability to translate, physical measures into, some consistent metric, money metric ideally, obviously. And so, for example, greenhouse gases, you know, the work that was done by that interagency group obviously is one approach to translating metric tons of emissions at the margin to economic impact. For water, it's a different challenge. Sarah and our co-authors and I had talked about that. You know, measure, for example, the opportunity cost of, say, desalinization of the ocean water. You know, but anyway, those of course are the great challenges. But we're more on the measurement challenge at this stage, just being able to quantify and measure trade-offs. As an example, we show in some of our work that the most likely version of a healthy diet for the typical American would use less fossil fuels, it would use less land, it would use less forest products, it really wouldn't reduce greenhouse gases, and it would use a lot more water. And so there are trade-offs, obviously, you have to consider.
Yeah.
That's why in particular, because fruits and vegetables are a key component of a healthy diet, and Americans should be consuming a lot more, and so that's going to introduce a lot more stress on the system, the water system in this case.
Yeah, just to follow up on that, you can go to the EPA and look at the Sustainable Materials Management Prioritization Tool, which kind of is an easy way to look at our USDA-IO model results. And if you look at some food products there, you'll see that they're the top contributors to some of the toxicity impacts that we have in the model, like ecotoxicity, and that's, you know, mostly driven by a lot of the pesticides. But fruits and vegetables in particular, which, as you said, comprise a healthy diet, which we're trying to increase our contribution to, you know, to the diet from a health perspective. But we have this problem, these other impacts that we do need to keep in mind when we're putting that. Yeah.
So, you know, quickly to comment to what Pat said, I think, you know, of course, I know your waste is supposed to expand to some other environmental attributes like what EPA is tracing model has, but you know, for the short term, you have greenhouse gases and you have water consumption. Greenhouse gases, as you alluded, we could put a dollar value there. If $54 per ton is gone, you'll put some number there to internalize greenhouse gases. The water you could use your price in different regions to internalize that. Of course, water price does not reflect the scarcity of water in different regions, as we all know. So at least for this tool, you have some good mechanism to internalize that. Actually, I have a question for Sarah. So this is kind of related to how to internalize that. My question is, Pat, earlier you used the two terms, value chain and supply chain. We know value chain is kind of convert everything to dollars. Supply chain is primarily on the physical amount. So the question for Sarah is, when you build the FEDS system, the top-down LCA system there, did you use value chain or supply chain? So what I mean is, when you build the GHG coefficient, water coefficient, did you use your grams per dollar or grams per a ton of vegetable grain moved? So which one did you use? I was not clear.
Sure. So we, in the FEDS model, we look at the value added through the supply chain in the food system. And so our unit of measurement is the grams per you know, liters or gallons for water, for example, or grams per BTU in the case of our fossil fuel analysis, but perhaps Pat could help clarify on this point.
No, you're correct, Sarah. So, right, because we link the input-output model to a consumption model, which measures grams consumed. We do develop these like greenhouse gas emissions per gram of consumption. And of course, consumption gets inflated to production through, you know, through the supply chain. And we ultimately do measure the total production, not just the amount that's consumed at the end point.
So in summary, you're based on supply chain, not value chain. For
That's
the
right.
okay, thank you.
I would like to respond a little bit to Wang's earlier comment about creating a complex index. We can definitely create a complex index by combining all different dimensional information. And there is a quite mature machine learning method. It's called clustering. So we can add all the multi-dimensional measures to the environment into the system, and we cluster all the different cropping systems or different activities based on those different dimensions. And we group different cropping systems to different categories, and those categories are from high, like more environmental friendly rank to the worst friendly environmental practice. So we can categorize all the different commodities or grouping systems based on multi-dimensional measures.
Thank you, Jing.
Thanks, Jing.
So Miguel, we got about 3 minutes left.
Yeah.
What I do want to say quickly, Jing mentioned that Pat and Sarah, in relation to the water use work, I do see Catherine Bierney is on the call, and we should point out, Catherine, while she is with West at EPA now, she was a visiting scholar at ERS and was very instrumental in developing that data. So I'm going to make sure it gets mentioned. But Miguel, maybe any just thoughts? I think Michael and Wes, we are all communicating, and I think that it seems that we should be, and I'm excited about, you know, that progressing.
Yes, no, and thank you, Wes and Catherine, for participating, because this give us even more incentives to, you know, to speed up developing a cooperative agreement that allow us to share data, share our models, and start integrating them, because I think this is the moment, you know, that as we develop, because our work, well, is always work in progress. We are always improving, but it will be a great moment to with intention do this connection. So I am very excited. The same with Michael, with Argonne group, and thank you for the presentations, because they are really giving us, as we see the presentation, you see the opportunities for integration that are many. So I'm very encouraged by this discussion.